So today, David Perez-Garcia will tell us about quantum position verification.
Okay, thank you. Thank you so much for the invitation. So, so first of all, important disclaimer, I'm a mathematician and I don't know much, if anything at all, about holography. So I apologize in advance if I say anything which is wrong or not even wrong. Please try to correct me, whatever, when I enter into holography. Okay, so, but I think it's nice. Of course, the connection with holography of quantum position verification is not mine, of course. But I think there is an interesting tension between some predictions by holography, thinking by holography, and how contradictory predictions using more quantum information. And I think it's a nice tension maybe to be resolved that one can learn from both sides. Okay, so this is more the sketch of the talk. I will first talk about quantum position verification. This is kind of the basic primitive of something which is called position-based cryptography. This is the problem of authentication. And from there we will enter into which is the adversary's view of that. So we'll play the role of adversaries. And essentially, adversaries must implement something which nowadays is called a non-local quantum computation, that I will of course explain what it is. And then of course the question is whether position-based cryptography is secure or not, or can be made secure or not. And this boils down to somehow bounding the resources that the adversaries need in order to break the protocol. If those resources scale exponentially, somehow the parameters of the problem, then one can say, okay, the system is secure, but if they can break it with polynomial resources, that's fine. So that's the question. So it's kind of an exponential upper bound, a linear lower bound. There's nothing in between. And now there are kind of two approaches. Some ideas from holography seems to suggest that adversaries can break all those protocols with polynomial resources. But there are some alternative point of view coming from quantum information ideas or techniques that were developed from this perspective that seem to indicate exactly the opposite. And then, of course, I think it's a nice tension that maybe benefit both worlds, but okay, the thing is not resolved. Okay, just I'll tell you which is the status. Okay, so that's the idea. And let's start with the problem of authentication. So, essentially, cryptography, Alice and Bob, they want to communicate securely. And one basic thing is that they need to be sure that they are talking to each other. In general, if we do like whatever, quantum crypto, BB84 or something, they communicate classical messages. They must be sure that the message they receive is from Alice or from Bob. They are assumed always to have an authenticated channel. Okay, the adversary can listen whatever is happening there, but they are sure that they are receiving the message from the right person. And I mean, this is a problem which is hard to solve in general because there is something which is called the man-in-the-middle attack. So my email we have here now. Evil guy. That's trying to really get a lot of money from the two. And he manages to intercept all communications between the two. So that for Alice, he pretends to be Bob. And for Bob, he pretends to be Alice. And there is no message passing through. So of course, Alice is completely convinced that she is talking to Bob. Of course, they will run whatever protocol, and they will create a secret key. But of course, Alice will be creating the secret key with the adversary. The same Bob. And of course, they will be very happy telling their secrets, but they will be telling them to the adversary. Okay. I'm totally convinced that they are doing something secure. Okay. And that, of course, is very hard to resolve. So one very nice idea that essentially goes back to Adrian Kent, beginning of the 2000s, and later was developed by Harry Woodman and co-authors, is to try to use like it's called, relativity-based quantum crypto. Essentially is trying to base the security on the fact that the speed of light is somehow constant. And with that, the idea is that, okay, based the authentication, let's say, the authentication in the GPS position. So, maybe you don't know if you are talking to Alice or to Bob, but you know that you are talking to someone which is in a particular GPS position. And only if you are there, you can really kind of pass the challenges. Okay, so the motivation for that, apart of course for trying maybe to resolve this authentication problem, is because that in some cases, like say, autonomous cars, autonomous drones or something, the important information of the car is not who is driving it or who is inside, but in which position the car is. So the cars talk to each other, and they would like to be sure that they are talking to this particular car and nothing else. Okay, so then there is the basic task upon which you can construct the rest of the cryptography, like secret key exchange and all that, is what is called quantum position verification. It's a challenge. Verification is a challenge that only someone in position P can pass. Okay, so that's the idea. So imagine someone is here in position P, and now there's some referees that and they send messages that position. Once the honest player gets the message, he has to answer back to the referees. And then the referees check two things that essentially that's important thing, that messages, SMS arrive in time. And in time means that, okay, it's exactly the time it takes for the signal to go back and forth, because one assumes, there's of course a very idealized scenario, that the computation that P has to do is kind of negligible with respect to the computation. So essentially, this referee requires that the message, okay, let's assume that all of them arrive at the same time at position P, and that the distance stays the same, for simplicity, doesn't matter really. So that the time the referee receives the signals is 2 times the speed of light from here to here. That's the, yeah, please.
Sorry, haven't you, the referees have to confer with each other, don't they? So
Yeah, the
haven't
referee,
you,
yes.
so haven't you just moved the problem to the referees conferring to each other that they agree on certain things?
Okay, it's a very good question, and the answer is yes. Yes. So we assume that the referees really are very powerful within themselves, and they just want to check so they can act. So that the problem, security problem, is around here somehow, and outside everything is kind of secure, and this is here where you want to deal, and you are totally right. Yes.
But it is fine that the referees are limited by the speed of light when they talk to each other. That's okay.
Yeah, in the end, yeah, that's totally
because
okay.
they can't instantaneously.
Sure, that's totally okay. So in a sense, the important thing, they can pre-agree on the challenge, do whatever they want, and then confirm later what they receive. Yes.
Like operationally, should I think of the referees as like the GPS satellites or something? So there's just like some small network of trusted referees, and you
Could, yeah, maybe.
But how can you trust that that these referees are actually the referees? Because isn't that the same problem with authentication? I'm confused.
In a sense, yes. Of course, this was kind of the motivation to this authentication. But of course, you are totally right. In principle, but in a sense, we will see that the man-in-the-middle attack fails here. So the referees are honest. We assume they are honest.
But the protocol is asymmetric, right?
It's asymmetric.
P cannot be sure that
Exactly.
he's talking to the referees.
Exactly.
So that the referees know that they're talking.
Exactly. It's totally asymmetric. This is what I was going to say. The referees are supposed to be honest here. And the whole point is to show that even you have several man-in-the-middle attack here acting, together, they cannot pretend for the referees to be in position P. That's the whole point. So it's exactly asymmetric. It's not, I made it symmetric there, but it's totally asymmetric. So the referees just want to check that they are talking to someone in position P. And the goal is to be sure that no one, instead of being in position P, can pass the challenge. Asymmetric version of that, like that. Okay. Any other question about the model? So, okay. Of course, going back to this, if you want to your question, one should be able to do this thing symmetrically, but it's crucial for all these protocols to work that there are at least two referees. That's crucial. So in particular, and in this sense, this will be always somehow asymmetric. Okay. But that's kind of the very basic primitive, and this is the one we will focus. Okay. And the motivation is exactly authentication of someone who's here. Okay. So for simplicity, let's assume that we are in 1D, which is the same as saying that there are just two referees. So we have lines. Exactly. Key. And now, as I said, the problem is, let's assume that we have here and here two potential spoofers that, of course, can act coordinately and, in principle, can also share entanglement, whatever they want. And together, they want to pretend that they are just an honest player sitting in position P and convince the reviewers, the referees, that this is the case. Okay.
So if I take away the quantum mechanics from this problem, because you didn't really put any quantum mechanics in so far, so what's known about?
I will go into that in a second. Let's assume that they don't have any quantum mechanics and the whole thing is classical. Messages are classical, everything is classical. So let's try to see a trivial protocol. So classically, this is impossible first. Impossible. So this, if it exists, if it's possible, must be quantum mechanics. Let me tell you.
To have a secure protocol?
Classically impossible to have a secure protocol. Yes. So to have a secure protocol. Okay. A secure protocol. And the idea is very simple. So let's do some sort of time-space diagram. So here is one referee. Here is the other one. Let's assume that the position is P. So they send messages. Then the answers. Okay. So it's supposed to be here. And now in these positions we will have bad guys. And then so the bad guy get the information here and the other one here. So what can they do? So it's very simple. What they can do is they can copy the information, keep it in memory, and send the other copy to the other. So they copy and keep one copy in memory for the future. And the other does the same. And then in this moment in time, the adversary at the left has all the information that the honest player has in this moment. So here he can behave as the honest player. The information that the honest player has to send to the right, he forgets and just sends the one to the left. The other adversary does exactly the opposite, so implements the honest protocol here. The adversary, the information that is supposed to go to the left, forgets and send the ones to the right. And of course, everything, the final outcome is exactly the same as the one given by the honest player.
Does this also work in higher dimensions?
I think so.
Because it has to be a bit more intricate. No? Because
Yeah, that's probably.
most of the messages they don't even get to see. So
Yeah,
someone
but
has
I think it's okay. Yeah. Okay, so that's a bit and this essentially is the the boxes because it's important. Maybe this diagram it will be like. So essentially, this diagram also tell us.
So the adversary has to make 3 copies, right? One sends to the, oh, no, 2 copies, yeah, one sends to the.
One kept in memory, the other
Okay,
sends to the
okay,
other one. Okay, so okay.
But sorry, so they also have to like capture the signal that's being sent by the omniscient player?
Sure.
Okay.
No, the
No,
idea
no,
is
no,
that
no.
the
Only the
adversary-
one sent by the referees. So in a sense, this is as you see this they are implementing like a man-in-the-middle attack,
Yeah.
but in an asymmetric.
But the idea is that there is no one, so in the case that there are adversaries, there is no honest player, right? So,
Yeah, there is no honest player.
yeah. So the signal that the.
Okay, or the
adversary-
yeah, okay,
adversary
yeah,
sends,
yeah.
it just sends it to the other
Or,
adversary.
or the honest player cannot erase a signal, right? So
Yeah, but they
basically,
probably
Yeah.
put this way. Yeah. Or just
So-
maybe this is slightly.
the signal always moves
slightly.
on.
Yeah. These are something this way, but yeah, that's okay. So as you see, I mean, the key thing of this attack is copy. One cannot clone quantum mechanically. So the idea is maybe if one uses quantum mechanics, let's say the signals are now quantum states, and the honest player is asked to implement some quantum operation. I mean, this attack at least will not be valid. Yeah.
Sorry, David, a stupid question, but how does the adversary know when he has to send the information back to the referee?
Okay, so no, the adversary gets so they are applying like a man-in-the-middle attack. So the referee sends a signal supposed to the honest player. Because the adversary gets the signal, copy, keep in memory one copy, and send the other copy to the other adversary.
So they know the distances, they know where they.
Of course, the adversaries know where they are,
the
of course.
distance.
They know where the adversary is.
So the whole thing is known. So essentially, for the adversaries, we are giving them the power to know when the referees will send the signal and which position the referees are trying to verify. And then they want to spoof that. Of course, I mean, you hide some of those information, but this is cheating. In cryptography, you have to give the adversary like the power to know the protocol they will run, when it will run, and all that. That's where we're giving them this power, of course.
But they don't even need it, no? They just have to wait for the second signal to come, and when it arrives,
Yeah.
they know that they're exactly at the second.
Is clear, Barbara?
Yeah.
Okay, good. Okay, so essentially, this is essentially now, the idea is let's change now the picture to the adversary's point of view. And then let's try to see what they have to do. So now, this diagram already tells us, okay, now, copy, they can maybe share some entangled state, of course. Now everything is quantum. Version. And now, this somehow is box. Models exactly the type of strategies that the adversaries can do quantum mechanically. So they will receive each a part of a quantum state. This will be the input to the game will be some register A for Alice, some register. So this will be now, okay, this will be Alice now, and this will be Bob. Because now, again, we are thinking in the adversaries. And now the adversaries are Alice and Bob, and they have to gain a challenge. So it's similar to these non-local games.
So sorry, before you have the adversary, the protocol can consist of correlated measurements or entangled joint measurements of the referees, or
Yes. The referees
the
are
referees can keep whatever message they get, meet later.
the referees are super powerful.
Measure.
They can keep quantum, if a
They can
quantum
break
memory,
quantum
they can
mechanics.
implement global quantum operation between the two. I mean, they can do whatever they want.
They're bound by the laws of quantum physics.
Yeah, of course, yes, everything is.
They cannot distinguish non-orthogonal quantum.
No, of course, everything is quantum. I will give you, I mean, specific protocols, but that's what they have to. So this is a quantum message here, quantum message here. They say some entangled state. Fine. And here they can implement any quantum operation they want, so any quantum channel between the quantum state, the part of the quantum state they have, and the input. Same for Bob. They can keep as much quantum information they want in memory, and they want to keep and they want to send quantum information to the other player. But this information, I mean, it crosses in there in a sense. They cannot do back and forth. So it's just one way from Alice to Bob and one way from Bob to Alice. And in this second moment in time, so there are two rounds, round one, round two, they can again implement a quantum operation, and then Alice will send register A and Bob will send register. So essentially, this can be seen as a game in which somehow there is an initial state. So, phi is a very bad psi, some initial state psi that is a referee Alice Bob. So this is the initial state. Then system A is sent to Alice. Going now from up to down. Sorry for the change of so this is down up. I'm doing the same down up now. Sorry. So system Alice will go to Alice. System B will go to Bob. They can implement. They have some tangled state, and then they can implement some joint operation. This is round one. They can exchange communication, quantum communication, and they can, of course, keep a quantum memory if they want. And now they implement a second operation, which is this is the communication step. And this is round two. And then Alice must send back A above B, and they expect to implement, I mean, some unitary transformation on A and B. So the final state is expected to be some global unitary in AB on the initial state. Of course, identity in the reference part.
Why is the round one a joint operation? Since the two attackers are separated.
No, a joint between Alice system and Alice part of the entangled state. So this is an entangled state. Small phi. And this is Alice part of the entangled state and Bob part of the entangled state. So phi will be the same, maximal entangled state. Some lambda I, Alice, I, Bob. Okay.
And I think that the attackers,
GI.
I think Alice and Bob can only act by a product agent.
Yes, Bob can. Yeah, exactly. This action is. Yeah. Let me specify. Yeah. Let me write the formula. Maybe it's easier then. Let me write the formula exactly. So the formula is exactly this. So they. So there is psi initial and the entangled state. We apply a unitary Alice on A tensor is sub A, sorry. Tensor, another unitary, different one in principle B, B. Then here they implement some kind of swap operation between the Hilbert spaces to implement, let's call some swap operation. This means that part of the Hilbert spaces they are kept in memory and other parts they are interchanged. It's the communication step. And then there's another U which now acts on B. Essentially, this S simply implements the following. So this unitary goes to the memory of Alice and the communication of Alice, which is of course the same dimension because I can purify, and then the message of Bob, so the memory of Bob, the communication of Bob, and then the swap is just the interchange the systems associated to the communication. and the rest are kept. And then they implement a second operation, which is a unitary on Alice memory, and the information that she gets from Bob, tensor, the unitary of the memory of Bob, and the information she got from Alice.
Could also be ancillas, I guess, no?
Then, of course, this is a purified system. You can put the ancillas on the entangled state. So in principle, they are able to do channels, but you can purify the full system. And then you put it as part of the entangled state.
And it's not entangled.
It's not entangled, but it's another quantum state. You will measure the dimension of that of it.
I would say just phi can be anything.
Phi can be anything.
Okay.
Particularly ancillas can be included.
You don't need any measurements because basically A and B can keep whatever.
Exactly.
Should
This goes
have
down
been
to
measured.
E again, and some other E prime A, sorry, and this goes to B, E prime B, and then this is the one that Alice sends back. And the idea is that this should be closed, all this should be closed up to some error to simply implement in a global unitary. Okay, call it global unitary U, and we call it P, because there are many U's now. This should be close to U A P A B on psi in and then some other state which we don't have to fight in that.
Basically, you care about the partial trace.
Yes, exactly. So we care about this part. Okay. And of course, this when you trace the rest, it will be a mixed state, but this mixed state must be close to a pure state in these two registers, which is exactly the pure state. But it's important, of course, that in each round, the axiom is a tensor product between whatever is in Alice and whatever is in Bob, and same here. Okay, tensor product. So when they act in a round, they can only act locally on the systems they have in that moment. Okay, so this is like a more sophisticated version of a quantum non-local game. Usually in a quantum non-local game, which is kind of a quantum version of these MLP star games, there is just one round. And that's it. And now we are giving them much more power. They can communicate in one way, Alice to Bob and Bob to Alice at the same time, and then do a second round. And the question is, what is the power of this type of protocols? Okay. Any question? Before we go to the next. So this type of protocol is what is called a quantum non-local computation. So this type of protocols, that implement this P. This is a quantum.
What is B? B is what?
B is the desired unitary that is part of the challenge.
The desired unitary is in principle a unitary
Between A and B, between A and B. A global unitary.
But the desired unit, A and B are not A and B, they are the ports in this case.
A and B is the quantum system that is sent as a question to Alice and Clayton.
A and B are not the adversaries, but A and B in that case are just the quantum systems, which even without adversaries.
Exactly. So of course, an honest player can implement VAB because in this moment in time, he has both systems A and B. So this is global, but of course, if the two systems are together, this is local.
The question is basically, are there VABs which you cannot implement this way? Right?
Exactly. Now, is there any global operation between A and B that you cannot implement in this one non-local way? Non-local means that you have two rounds in which you can do things which are just local, but you have the power of having entangled states and quantum communication in one round. And this is called quantum non-local computation. This is exactly this. Okay. So let me now tell you what is known about that.
So for now, there's no bound on anything, but
No.
there's
no bound. So the question is, for the protocol to be secure somehow, for security, we would like that the resources to implement V in a non-local way so this way scale exponentially with the dimension of A and B. We can assume that for simplicity. Okay?
Is it even obvious that if you wanted to do it exactly, it's possible to?
It's a very good question, and yeah, the answer is exactly no. Exactly is impossible. There is always errors, but approximately is possible. Yes, that's the first result. Yes. So, but the first result. So now exactly. So that's the question. And then the question is okay whether it is even with unbounded resources even possible. The answer is yes.
So the point is that with a suitable gate set, honest party can do this with polynomial resources, right? In the dimension.
Okay, this is another desirable thing, which is about efficiency. But we can't even don't care about efficiency so far. This is even.
No, but you said exponential. Oh.
Yeah.
But this no. Okay, or by resources, I sorry. By resources, sorry. By resources, I mean somehow in this case the dimension of the entangled state.
So you don't look at the cost of implementing
No.
a crazy complicated unitary method system.
No.
Is the dimension or the log of the dimension?
Okay, it depends. We can measure dimensions or number of qubits, whatever you prefer. In both cases, if one is exponential in one is exponential in the other.
But of course, in the end, you can do any gate in a scaling polynomial in the dimension of the space. Right? So if the
Yes.
spaces are small, you can definitely also do it computationally efficiently. Given a gate set with a continuous angle, right? So
Yeah, but this is okay. It's a very important question, of course. In order for so there are two things one wants. One is that for the honest player, the protocol is efficiently implementable. And second, that for the bad players, those implementing local computation, they require exponential resources. But even if you ask to implement, I mean, if you give them the possibility to implement exponentially long computations, now we are talking about resources in space, not in time.
there's also long computations.
Okay? Even that case is not clear at all. And now,
you say there could be a unitary, which in between you have to go to a very long computation on many qubits, maybe.
but the thing is that here they need exponentially many space, quantum space. So it's now we are trying to bound not the time but the space. Okay, that's what I'm saying. And the reason is that if you have enough space, you can simulate that with no extra cost on the time.
Okay, but so the long computation, you can only do it if you have a system to run it on, right?
Yes.
I don't think otherwise.
What I mean is that I would not assume that V can be implemented efficiently for the honest player. Can be any global unitary up here.
But again, if the dimension of this phi is polynomial, then any unitary is efficient. It's just a polynomial-sized matrix, so you can write it down. Unless you specify it implicitly. I'm not sure. Are you thinking of something like that V is not specified explicitly in some way?
No, but I mean, one can think in number of qubits. Imagine that the input is n qubits. And of course, V could be as a function of the number of qubits exponentially complex.
Yeah, okay.
And now this will have exponentially many qubits. Fine.
So you mean exponential in the number of qubits, not in the dimension of one.
Yeah.
That's exactly. I think I'm confused for a similar reason. Like, what are we using? An exponential dimension of phi is kind of just a polynomial number of qubits. So.
No, but this dimension is also dimension. So So this is not number of qubits, but this is the dimension.
This should scale as well, so.
Yeah, of course, it's about the scaling. Yeah. You have a family of protocols about the scaling, yes.
So those are really.
You can do the scaling or with the dimensions or with the number of qubits.
And those
Of
are
course,
really.
both you have to measure with the same number, otherwise it's.
Those are already an exponentially big Hilbert space, basically, right?
Yes.
Okay. So it's not the Hilbert space dimension, which is a relevant parameter.
No. Yeah,
The log of the Hilbert space
If you
dimension
want.
is kind of the relevant parameter.
but you have something exponential, it's the same. Okay. But yeah, you can say you can measure the number of qubits, which is log of that. Okay. Okay, so the reason I always think in dimensions is because of the techniques we use. I would probably not have time to that, but we use from the quantum information. Dimension is a more natural parameter to play with, simply. Not log of the dimension. That's why. I tend to think this way, but it's just okay. Okay, this is what we like. And then going back to the question, so essentially what it was shown by Bayesian and Kenny. In 11 is that somehow with exponential resources, with exponential dimension, exponentially many qubits if you want, exponential many qubits, exponential dimension, you can implement any behavior.
With very small error.
Exactly. For a fixed error, for a fixed error. For any fixed error. So in all these protocols, getting a constant error is perfect. So this epsilon we can think as a constant 0.9%. I mean, not the error. The error is the opposite, 0.1. Sorry, I was thinking the fidelity. It's 0.1. So fixed error is enough.
But small fixed error.
A small fixed error, yeah. But even not the small is okay. It's very hard to get even non-small ones. I mean, it's 0.3. Not only it doesn't need to be.
So it doesn't have to be.
Important because it's about the scaling, keeping this going. But yeah, for fixed error, this is exponential. And the idea is kind of by what is called port-based teleportation. Which is a nice version of teleportation that has the caveat that uses exponentially many EPR pairs. That's where the exponentially come from. So what is the port-based teleportation? So the problem of teleportation is that here, one has to be very careful with the communication you have. Let's think we are the adversaries, we want to optimize our strategy, we have to be very careful because we only have one message to one time to send messages, that's it. Because one possibility to break the system would be, okay, Alice teleports the system to Bob, Bob implements the global unitary, sends the system back, and we are done. But of course, the first part of the teleportation is a measurement in Alice. That's totally okay in the first round. But for Bob to correct the error, Alice needs to send information. And that's very bad because you are losing a lot. You are already wasting your communication on that. And then, of course, Bob cannot send the system back. There's no possibility to do back and forth. If Bob could somehow, if the teleportation could be done without having to correct, then Bob could implement the global unitary here. In general, of course, this is kind of impossible, but there is something very nice one can do. This is this port-based teleportation, which is the following. Port-based teleportation, Alice and Bob are assumed to share many EPR pairs. Let's assume this is, I call it EPR of dimension D, which just means the maximum entangled state of dimension D. And they have some state here, they want to teleport unknown one, which of course is D-dimensional. Okay. And they have many ports. So a port, so these are just copies of this maximal entangled state. They are called ports. Each one of these copies is called ports. And there are, K of them. Okay. And then this port-based teleportation, Alice will implement a global measurement there. Okay. Particular one. And then what will happen is that psi will be teleported to one of these ports, but exactly without the need for correction. And what is not clear, what Bob doesn't know, is to which port.
Is that with high probability or?
There is an error. I will talk about the error. And then the information Ali has to send Bob is to which port he has to look. And this can be done with an error, which is of the order of d squared over k. And here you see the exponential scaling. Now d is dimension, and k is number of EPRs. Okay? So for this to be order 1, the number of EPRs must scale with the dimension polynomially. So you have in dimension and exponential scale. Okay?
Sorry, I don't think I fully understand what goes wrong with naive teleportation. So Alice gets some register and then teleports it over to.
Yeah, but there is not a real teleportation, because if Alice really does the teleportation, says how to correct.
Yeah, so he just sends him the all the measurement outputs, and he's got some unitary.
Yeah, but then you don't have, time is gone, because they arrive at this position in time and space to the other side. So now there is no time.
Yeah, I see.
For this to send back the other system. So in a sense, one has to be very careful. One has to correct in advance.
So they can do one proper teleportation, right? But
Exactly. This is exactly what will happen. So okay, this is possible. Okay, so then what will be a cheating strategy?
Sorry, I haven't understood how they succeeded already, so
Oh no, this is possible simply. There is a result. Okay. Sorry.
Let's assume this is possible. So what do we do now?
Exactly, I will tell you with this how to break.
Good, sorry.
Exactly, I will do that. Exactly, so exactly this now. Exactly. Why this is useful for that. So let me then tell you how to implement any global unitary like that. So what we'll do is in the first round, Alice. Okay, so Alice. So we have one entangled state first, Alice system. So now Alice will do the measurements for a normal teleportation. And there will be some correction, which is some Pauli matrix. Okay. This is Alice system. This is, okay. Whenever I do this thing, this means EPRs. Okay. So this is Alice system. This is Alice. So if Bob could correct, and this is Bob's system. Okay, they are entangled with the referee, but I will not draw these lines. Okay. At this moment in time, here, one has Alice system up to the Pauli correction, which is totally unknown to Bob. But what Bob can do is take these two systems together and do port-based teleportation of these two systems back to Alice immediately. No, they can be done independently, no? Because this is these two things Bob have. This is
Bob is not doing a unitary or so. It's just
no, just sending back. So now everything this is round one. I mean, look that all these things can be done in parallel. No? Alice measures as a normal teleportation, and in these two systems, which this is the same part of the API that Alice is using for normal teleportation. These two systems, Bob port-based teleport back to Alice.
The point is that they end up in the same port. That
exactly.
If you wouldn't do that,
exactly.
this wouldn't happen.
Exactly.
Because it feels like overkill teleporting both ways.
No, but this
That's the
crucial.
point, no, because you
Yeah.
get it in the same port.
Exactly.
And otherwise you don't know which port. it is.
Exactly. You have to do the global military defense. So now,
That's
okay,
smart.
so they do now, okay, for that they need EPR pairs of square dimension, okay, of course. So now this system is port-based teleported to Alice. So in these many EPR pairs that Alice has, together with Bob, these two, okay, there are two of them, these two are in one of them. Alice doesn't know in which one. But there are two systems here. So there are two systems. One corresponds to the Alice one corresponds to the Bob one. Still in the first round, Alice can, in her part of this port-based teleport, undo the correction, or do the correction. Sorry.
So she does the correction on each port.
Exactly, on each port, on the Alice part of each port. And after doing the correction on each port, she implements the unitary V. So in each port, sigma identity in Bob, sigma I of the Alice part, tensor identity in Bob, and then VA in each port. So now in all ports,
And this is still round one.
round one. There's no real communication going on. And this is end of round one. And now what happens? Now Alice sends as communication Bob part of each one of the ports to Bob. And Bob says to Alice in which port the port-based teleportation succeeded. And this is the communication that they send. So after that communication,
And this could also teleport.
but but after that communication, they just have to keep the right port.
Become classical.
Sorry?
It's become classical at that point, huh?
No. The information from Alice to Bob is quantum. Alice has to send Bob part of the.
Once they've projected on a port, they have only, then there's still one EPR.
They have some entangled state, which is is this they have this entangled state.
But they could do with classical communication, right? Because
no.
Alice could teleport Bob's part to Bob and then they just send classical messages.
Yes, that's definitely true. Of course.
If they want
Every
to
quantum
make this-
communication can be done with classical communication and entanglement, as we know. So of course they could do that. So essentially, that's so this is the first part. Then Alice sent ports to B to Bob, and Bob sends which port to look. And they just restrict to that. But I mean, it's crucial for Alice to implement this in all the ports, that somehow these are clean, in the sense that there is no correction from whatever Bob does in those ports. Otherwise, Alice couldn't know how to correct first. That's why this is very important to have this port-based implementation. But of course, the price to pay is that the number of EPRs grows, the dimension of the entanglement grows exponentially with the dimension of the. Is it more or less clear? Okay, so let me.
Why does Alice have to teleport? Couldn't she?
Just the all the both part of the ports.
No, I'm saying why Alice has to teleport
Ah,
in
so
the
that's
first place.
Because otherwise she has to implement a unitary between her part and all of the ports. But this unitary don't commute with each other, so one has to be very careful. In this way, they are kind of independent.
This way the A and the B part are in the same port, which part they're in the same port.
Yeah, please.
Oh, first question, is there like a simple way to describe what you do in the port-based teleportation, or is it very complicated?
No, it's not difficult. Okay, I mean, essentially the idea is you can have kind of this state. So this EPR pairs, and then what you do is you consider you trace each one of the ports. You define eta I as all these maximal entanglement states, or these EPRs, the tensor And then you trace only in both part, only I, all but I. All but I. So you just keep one of those parts and the rest. And then this will succeed. And then if and only if you could distinguish between those states. This is not difficult to see. What? You could
measurement.
Sorry?
That's not a measurement.
No, exactly. If there exists a measurement, that you could distinguish. And okay, there is some. Because in a sense is that you can, by acting here, you can distinguish the points. So it's okay, there's a lemma that tells you that essentially, if you could distinguish these states, or distinguishing the ability of distinguishing those states is the same as the ability of doing this. And then you implement this pretty good measurement here to distinguish between these things. And that's essentially what you have to do here. I mean, the connection of this distinguishability with the teleportation together with a pretty good measurement to distinguish those states. That's it. It's very well explained. In the original paper, it's not, but in this paper, it's very well explained.
And for like the exponential resources, I guess it really is dimension, right? Because like you have to set k here to be like, I don't know, like 100 d squared. And so then the dimension of the EPR pairs would be like d to the 100 d squared, which is exponential of d.
Okay, I have to think on that. As I said, I was thinking dimensions.
Yeah, that's right.
So psi ends up in one of the ports. And
Sorry?
the other, psi ends up in one of the ports.
One of the ports.
And in the other ports, some uncontrolled thing.
Exactly. Trash. Yes.
What is the communication and then between A and B?
For that,
Yes.
just which port to look.
But that's much more than we would get in normal teleportation. We need much more communication.
Much more with respect to that, much less with respect to the entanglement. It's log, the dimension of the entanglement, what you have to send, and it's more than this. But you have this absence of correction. That's the nice thing, and this is crucial for that. Indeed, there was a previous protocol by Harry Gurman and company in which they did just normal teleportation back and forth without this promise, and it was double exponential resources. Which you have to keep teleporting the errors, not that all the time. Oh, wow. Okay.
Also works?
Also works, but double exponential.
It's kind of remarkable that this works.
I think so. Okay, so let me, because I'm running out of time, I would like to do the connection with holography, at least. So, okay, so what is known? So this already tells us that with exponential resources, this is doable. So this tells that essentially with exponential resources, okay. So now there are some protocols. Let me describe one very fast. For which require at least linear entanglement. Okay, and the protocol is what is called, one of them is called F-routing.
F.
And this F is a Boolean function on two bit strings. Okay. 0 and 1 are just strings of bits. And then the X together with one state of one qubit is sent to Alice. Y is sent to Bob. And what happens is that the qubit must end up in the left or in the right, depending on the value of f. So here, if f of xy is 0, and here, if f of xy is 1. So the value of this function that depends on the classical input of Bob, Alice, and Bob decides where to reroute the qubit from the left, to the left or to the right. And one can show, okay, so not trivial, but one can show that there are f functions which require linear entanglement, linear with respect to the dimension of the input, which is already exponential in n.
So what you're saying is that to break this, you require this linear,
Yes.
that is, the algorithm is not known.
No. No, but so I mean, one can prove that with less than linear, there are functions for which you cannot do that.
Linear in what?
Yeah, number of qubits will grow linearly with it.
And sorry. you said-
N is the size of the questions.
Okay, and that's exponential in the Hilbert space then.
No. The Hilbert space dimension is exponential in n because but they are classic. I mean, this important thing here that
It's classical bits, so it's n bits, you're saying.
N bits.
So the Hilbert space, okay, it's really n bits, qubits, whatever.
exactly we'll not make distinction between bits and qubits. If one does, this is very nice because in this all the resources are classical. There's one single qubit, but in order to break that, you really need quantum dimension, which is same as the classical dimension.
Is a function something simple or something?
No, there's a very good question. So first proof is that there exists a function, and this is accounting art. Together with the fact that one can reduce the entangled state always to be the embezzlement state, which is also not the embezzlement state, which is also not trivial. And then it's accounting art. But there is a very recent result from people at Perimeter, like Alice May, and Richard Cliff, others I forgot, in which they prove something like that for the inner product function. So if the function is just some xi yi mod 2, what they can show is that the adversaries require at least a linear number of gates in n to be implemented. So for this, the number of gates of the adversaries is omega of n. Okay, so this is of course a pretty simple function. But the one that computes the entanglement, this is just existence proof by counting.
So this is really just the gates, but not the module.
Exactly, these are the gates. Okay, so let me just say a few things about holography. So essentially, okay, so this tells that the upper bound is exponential. So with exponentials you can do anything, and there are lower bounds which are linear. For some protocols you require linear. And the question is, there exists any protocol? I mean, what happens in between? I mean, exponential everything, linear, whatever. I will not be able to tell our results that indicate that really exponential is the right thing. But they are based on some techniques from functional analysis.
But your results are saying that there is an exponential lower bound?
Under some conditions. Under some conditions. Of course, if we could do it unconditionally, the thing was solved. So we impose some conditions on the adversaries. And essentially what we impose is that the attack of the adversaries depends somehow smoothly on the V to be implemented. So for different Vs, there might be different Us. If you change slightly the V, and then you say that there could be an attack in which U will be similar but change also slightly, then you require exponential entanglement.
Is that a reasonable assumption?
It's a very good question. So of course we did this for discrete number of Vs, and then we can index by the strings, essentially the diagonal matrices with plus and minus ones in the diagonal, but global ones. And then we can show, for instance, that if this, just for the first round only, whatever they do can be well approximated by a low degree polynomial on these bit strings, then you require exponential entanglement.
What do you mean by low degree? Like scaling in some way?
Polylog degree. So that's, and there is some nice conjecture somehow in the geometry of analysis spaces that would imply the exponentiality without any hypothesis. But okay, this is about the geometry of the unit balls of subspaces when you cut a unit ball. That's something I would not have time to explain. And there's another thing is that if one assumes some crypto things, like the system of quantum random oracle models, one also requires exponentials. So okay, there are several indications that, yes.
So David, I mean, the first result, would this also mean that if you pick now out of your family of Bs, them randomly, then you would need an exponential?
No, why? Because the attack can depend in any way from that, as a thing you can. No, not really.
So that you somehow enforce that the U has to be also smooth.
Yeah, that's the thing. That's the whole point. We thought that we could do that by some, typical thing that regularize things, like doing convolution, things like that, but all these approaches fail so far. So it's not clear. Yeah, it's not clear at all. But that's the thing to try. Okay, so let me just I'm sorry, 5 minutes about the connection with holography, because now what holography seems to indicate is that indeed one should be able to break all these, or implement, let's say, quantum non-local computations, so break the position verification schemes with only polynomial resources. I think this is nice. Yeah, this part is of course the part that I hope not to say many stupid things, so let me just briefly sketch. This is done in a paper by, it's better to go to the paper, Alex May, and Pennington, Jonathan Source, years ago, around the 2020, I don't remember exactly. And the idea is that this is a boundary, and then there are kind of two positions, S1, S2, which are the sender positions, and two receiving positions, R1, R2, receiving positions, okay? And it could happen that in the bulk, there is a point P, which is in the future light cone of the senders and in the past light cone of the receivers. Okay? So there exists a P in this intersection of light cones.
That's assumption.
Assumption. But there does not exist such a P in the boundary. Meaning that if I consider these future and past light cones of the boundary, the intersection is the empty set. So the future light cone of S1 intersection future light cone of S2 intersection past light cone of R1 of R2 is the empty set in the boundary. So if there is a nice boundary correspondence, anyhow, this action, which is the action of the honest prover, in which in P one implements this V, well, assume of course that one has in P a universal quantum computer or something, must have a boundary reflection. And if one looks from the boundary point of view, one gets exactly a non-local computation pattern. So something exactly like that. And now one can then say, okay, which is the ratio between the number of qubits that can be sent through the valve without changing the problem, so that the geometry doesn't change by a reaction or things like that, whatever this means, and the entanglement, number of qubits of this sent to the valve, And this is exactly the exponential of that is the dimension of the system's A and B versus the number of qubits of entanglement. And it seems that the below thing by Ryuta Kayanagi should be essentially disorder, this means, and the above thing should be like this to the power alpha, for any alpha sticks smaller than 1. And therefore, this is a quasi-linear polynomial, it's polynomial scale. Unfortunately, I cannot say much more. I mean, I wanted, but it's nice that I'm running out of time, so I cannot. I don't need to say more things. So I'll probably ask enough questions. I should probably stop here, and then I'm free to answer more questions. Thank you. Yeah.
Sorry, what was the second proof you said? So you can prove it like using a smoothness condition?
Yeah, sure.
Okay. What was the second condition you said you were able to prove it?
Okay, so there is So there are two things there. So since there, what we try to implement are kind of the V we are going to implement or going to implement are diagonal matrices. Ij, epsilon, ij, ij, ij.
That's just ad hoc, or is that the good reason to look at?
Exactly, because we have the tools to analyze these things.
Okay, but it's not clear that it's.
No.
Simply
Simply
say for.
no, because of course then of course this is a function of a element in the Boolean hypercube, and then we have a way in which we can understand the value of the gain associated to epsilon. So this means, which is that this is the optimal probability of implementing this unitary with non-local resources. This, of course, will depend on the dimensions. It's a function of the dimensions. And then we are able to show that this is approximately equal to a very nice norm in the tensor product of many Hilbert spaces. Okay? Essentially, all those which are involved. It's B, H entanglement A, H entanglement B, tensor 4. And this means that the norm is in each one of the tensors is just a Hilbert norm, and the norm is what is called a tensor norm, that it is compatible with the tensor structures. These tensor norms we defined by Grothendieck in the 50s, and they are very nice. And now what we try to say is, okay, the things that one can really compute, okay, this is the norm of some tensor that is related to the game. And now, these things, there are many techniques to estimate those things. So, if there is a strategy that wins the game always with some probability, this must be, because of course the same is true for all of them, let's say 0.9. And now, what we can prove is that under some conditions, get an upper bound, which is essentially, let's say, what is log of the entanglement, sorry, log of, let's say, the entanglement dimension divided by the dimension of A, essentially. I mean, roughly speaking, this. Of course, if this must be bigger than a constant, we have an exponential. And of course, for that, if we need to use many tools from what is called the geometry of Banach spaces, where there are many tools to estimate these things. One can use, in fact, harmonic analysis on the Boolean hypercube, there are many tricks one can use. And this is more or less where we get the exponential. But for that, we need that the actions, the dependency on the actions of epsilon can be well approximated by low-degree polynomials. This is one thing. This is one theorem. And now the second one is based on a nice kind of conjecture. So take essentially this norm. This is the dual norm, but the dual norm will have the same case. And take the unit ball of that norm. Okay, this can be some very clear object, can be. Doesn't need to be even round, okay, some ball. And now we look inside this ball for the largest Euclidean ball. So the largest ellipsoid, the largest in volume, that can be inside. And we compute the ratio between this and the volume of this ellipsoid. And now, okay, this is of course something which is not properly, this scales, of course, if I multiply by lambda, this goes to the power n. So of course I by the dimension, so that this is now a dimension less constant. And this is called the volume ratio. Okay, so if this cannot increase if you go to subspaces, the same for a subspace. Okay. This means that now I cut this ball by some hyperplane and look at what happens there. And then up to log corrections, you cannot get something higher. Then one needs exponential resources. of course, this is in general false, but one expects this to be true if this norm has enough symmetries, because of course you have a lot of symmetries, and you take a subspace, then it should be similar to the original case. This norm has a lot of symmetries, but it's an open question whether it has enough symmetries to fulfill that. We could prove it if instead of 4 copies we had 2, but with 4 we don't know how to prove it so far. That is a kind of a condition which has nothing to do with the original problem. It's a problem about the geometry of balls. And if this is true, then one needs also exponential resources without any hypothesis on the strategies. That's the second result we have. But okay. And this together with this result of Dominic Unruh, that with the quantum random, if one believes or one assumes that one has a quantum random oracle model, then the adversaries also require exponential resources. So this is also proven. So there are these many things that indicate that maybe exponential is the right thing, but holography predicts something different. And then I think it's a nice tension to be resolved. Either holography gives rise to attacks, which one cannot come up with without these ideas, would be fantastic. Or exponential is the right thing, but maybe this tells something about holography. And one can try to use all this, one will have, access to use all these sophisticated techniques in holography. Suddenly you might be a disconnection. That's a bit why I find this very interesting. Sorry, Ignacio.
No, I wouldn't say it would not be fantastic, it would be very bad because then secure, it would not be secure.
That's fantastic, meaning that would be a nice protocols coming from holography.
I think in this case, with the random epsilon ij phases, you said that something had to be assumed about the unitaries.
Okay, there are 2 results. Under this conjecture is without any hypothesis. For this to be true, that will require also exponential resources. This is true only if the unitaries implemented by Alice and Bob in the first round can be sufficiently smooth with a particular definition, which in particular this definition is fulfilled, is this can be approximated by a low degree polynomial in epsilon. Up to additive correction. Made it by low degree, and low degree means polylog. Low degree polynomial.
This doesn't mean the test will necessarily be smooth, right? Because the epsilon is just ±1.
Yes. Okay, there's a notion of smoothness, sorry, which is a discrete smoothness. One can compute a discrete gradient, and smooth is that one has a bound on the discrete gradient in average.
I don't have much intuition for this. Like, do you think this is a reason? I mean,
no, it's a good question, and I don't know. Okay, maybe the other is that you have a nice bound on the discrete gradient in average. I mean, of course, you can define a discrete gradient. You just simply switch a bit and take the difference divided by 2. And then this is the partial derivative. And then the expectation of the norm of the gradient. Having a nice bound on that is what you really need. But for instance, if you have a low degree polynomial, you can bound this. Of course.
But you also have a conjecture that does not require that.
Exactly. This doesn't require any of these assumptions. If this conjecture is true, no matter which is the strategy, must be exponential.
So the implication from holography is that you cannot implement V in the bulk theory. The bulk observer cannot implement those V's.
But probably. Yeah. For instance, one possible way out, and probably it's very good, is the reasonable for one is in this approach, indeed, the operations that the honest player must do are highly complex, because of course they are random.
Yeah.
And of course they will be highly complex. So it could be that, of course, if here you need exponential time to implement this, the whole connection breaks down. This could be. But this is just simply coming from this approach we have. Could be that same is true with efficient here, this side, this. So this is definitely a possible way to reconcile this, assuming this conjecture is true, and that is that here we will be dealing essentially with non-efficient gates, because they are random gates essentially. And maybe this somehow breaks down already the whole connection here in this I don't know. But there must be something about the complexity of the gates, of the unitary to be implemented.
But suppose we assume that V is low complexity, which is something reasonable to assume for an algorithm.
Yeah, of course. I mean, this of course is what we would like to have, definitely.
Yeah. So in that case, there is no argument about.
No, all our arguments simply break down. There is no argument. Okay, the one based on the quantum random oracle model, this is efficient. But then, of course, this is like a cryptographic assumption that this is that you have like an oracle access to perfect hash functions and things like that. I have no clue how to introduce this in holography, this kind of cryptographic assumptions. But in that case, this is efficient. And for these F-routing protocols that you have to reroute, in principle, there are no, as far as you know, no arguments that they could not maybe require even exponential. This is the best they can prove so far is linear. It is also not obvious how to implement holography ideas to make rigorous attacks. Because if one uses toy models, they also are not good enough for that. It's also not clear how to go the other way around. So, I mean, I read, because I'm trying this approach, I tend to believe that exponential is the right thing, but of course, this is just a totally biased opinion. That's...
I guess the bulk observer in holography might have some trouble implementing anything very interesting if G Newton is very small, because they can't do very strong interactions. Maybe they have to make, or maybe they can make it out of little black holes or something, the computer that is implementing V. Like, naively, they can't do a lot of good computations with simple ingredients if G Newton is small, because things just don't interact very much.
Well, you could have a small G Newton, but strongly interacting matter.
I guess don't people have trouble? I mean, well, there's some conjectures you can't do that. It's at least the topic of conversation in the bootstrap, right?
Well, let's say the standard model, let's say we were living in negative cosmological constant, right?
Yeah.
And the interactions of, let's say QCD or QED are very strong compared to gravity. Now you could say maybe you can't realize the standard model.
Well, it's at least a topic that people debate, right? In the small plan bootstrap, the intersection of those communities, they
okay.
Yeah. So if they would be happy if you have a theorem that they can't have
Well,
it.
they say gravity is the weakest force, so there can be stronger forces. That's one type. I think to Pennington, of course, if I remember, the abstract setup that you had with the two adversaries can be implemented here and would be a possible boundary algorithm. Well, they didn't claim that it was bulletproof, that whatever can be achieved in the boundary in this setup is modeled properly by that abstract setup.
Okay. Yeah, maybe it's true. Maybe they at some point Alex told me that maybe there is some extra thing they could even use, but they think that indeed this shouldn't be useful or something. But I don't know exactly which was the exact. Because there is some. If you draw the light cones here, there is some intersection middle point, which is something could happen, but I really don't know. Yeah, I don't know. Maybe. Unfortunately, I don't know anything really about these things so in depth. So my knowledge is very superficial. So, but the claim you say is that in the boundary they have more power than that.
Well, they didn't have a clear proof that they didn't have more power.
Okay.
They had at least as much power.
At least as much, but they could have more, and there would be another way to solve the problem. Okay, I see. Okay. So maybe okay.
There's one conceptual question I have about the comparison between this and that. So when we say, so here we're assuming we have a full quantum field theory, and when the entanglement in principle between the two is infinite because we have some UV divergences. So how Okay, I'm not sure how this number of qubits entangled.
You are totally right, because of course, there you have like a bound on quantities like whatever entropy or mutual information or things like that, which are maybe bounded by something that depends on this, but not in the number of qubits. And that's, is this your question?
Maybe I'll ask perhaps in a more clear way. So in the previous discussion, there were these adversaries that were localized in space-time that had maybe some amount of. Here we have a quantum field theory which is delocalized space-time, right? It exists everywhere between the two adversaries and maybe even beyond where the adversaries live.
So the point I felt, of course, again, I mean, maybe I'm totally wrong in my understanding, is that if one draws this part here, of course, I mean, they do have, maybe not exactly, but something similar to this. But of course, everything in general is like infinite dimensional. That's true. But somehow I think that I mean, you understood it wrongly, but the key quantitative argument is here. But of course, I have no clue how rigorous is to say that one can design a protocol in which you send effectively this amount of qubits to the back of the boundary via, I don't know how, in the continuum limit, and that you have really a quotient between a measure of entanglement, of course, in this case, I don't know, this number of qubits, or should be some information or something, that really is something, at least for finite ends, which is something finite. But I have no clue, of course, whether this is
maybe let's
true or not.
Differently. So in the previous discussion, there was some entangled state, and there was no Hamiltonian acting on this entangled state while they were doing this experiment. But here somehow we have two pieces of the CFD, and they are coupled to each other in order to evolve the CFD.
Okay, I see what you mean. So there is like a background global evolution going on. But this,
yes,
is this what you
somehow
mean?
the CFD is part of the space-time where these adversaries live in, and the field theory is connected between the two adversaries, so it's not as sharply separated as it was before. So okay, that comes about.
No. Unfortunately, probably I'm not the person. But Alex, maybe we'll come to the program at some point.
Yeah.
For sure, he knows the answer to that. Unfortunately, I'm not the person to ask. I'm sorry.
Okay. There are no more questions. Let's thank you.